Hi everyone, and welcome again to this webinar. Today we are going to see tank cooling and processes cooling, in which we'll search an essential guide to calculate these processes and tank cooling, focus on agri-food industry, ensuring that the correct size. Welcome again to this webinar. Ensuring the correct sizing of the cooling equipment that we will need to the case of study that we have been prepared. So let's see. Let's dive into this program today. And first of all, I want to tell search an history that the late 19th century, drinking milk was almost a game of chance. No one knew whether drinking milk could make you still be sick because of bacteria and different proliferation of viruses. So all of this because of there wasn't any effective way of preserving milk. So we were really faced with food insecurity that led to serious diseases, mainly in childhood. We always have to face economical problems and food losses too. Was then when Louis Pasteur discovered that by applying heat and cooling and control of the temperature in the process, we could eliminate microorganisms without altering the quality properties of the milk. So that was when pasteurization was born. An application of a thermal process and a cooling process to avoid spoilage of the milk. So today let's see the contents that we are going to show with you. In the first part, we're going to see the agri-food market drivers, different applications for processes cooling. Next, the essential guide on tank and process cooling calculation, how to calculate tank cooling and how to calculate thermal processes. And finally, we are going to dive into Client 360 to search a project that we have been prepared. So let's see the main drivers. First of all, we think always on food safety and health regulation due to agencies such as FDA in the United States of America or EFSA here in Europe, who imposed different standards for preservation the preservable foods. So next, we could know about consumer trends that want fresh and minimally processed products. Customers are increasingly demanding this fresh food and natural products without preservatives. So this increase led to a need of the cold chain to preserve this temperature along this chain. Next, processes automation and digitalization, where industry is transforming the agri-food sector, keeping it control, an holistic control of the variables that are included in the process. So a better management software could help to optimize the processes and the preservation of food and the energy waste. We could also have a market driver that is focused on energy efficiency and sustainability, where the reduction of energy cost has driven the agri-food industry to look for more efficient refrigeration systems. In addition, customers buy products to companies which try to align his sustainability value, the core of the company, that vision. Finally, we could see the globalization and logistics in the cold chain. We have mentioned before this globalization here. Agri-food products must travel along distance while we must maintain the temperature in the cold chain to preserve the perishable food. So some examples could be the milk sector, milk market, where the temperature control is essential to ensure those microbiological safety and maintain the organoleptic properties. So different applications in tank coolings could be the raw milk, where you have to cooling this milk after milking the cow to 40 degrees, more or less. Condensed milk, where we need cooling after the concentration processes to avoid that crystallization of sugar. Other example will be liquid yogurt to preserve cooling, the cooling in tanks to stabilize the product before packaging it. Oil market, it's quite spread. The thermal control in the production of vegetable oils is essential to avoid the oxidation of the product, the olive. For example, could be extra virgin olive oil, where we need to cooling it up to 15-18 degrees in stainless steel tanks to preserve the properties. Or even sunflower oil, where we need to maintain the temperature control to prevent rancidity and the formation of unwanted waxes. Next could be wine market, cooling the winery processes, such as different controls, fermentation, cooling processes, maintaining processes are needed in this market. Different applications will be white wine, cooling of the most at first before fermentation to improve clarification and prevent oxidation. Red wine to maintain the control temperature during deep fermentation too. Optimize the color and the tannin extraction of the red wine that is very, very typical in this product. Other market, broth and soap market, must be cooled rapidly to prevent bacterial growth and ensure safe preservation before packaging and distribution. So after boiling the soup, we need to decrease this temperature from 100 degrees up to 4 degrees in the shortest possible time. Other application, beer market. Cooling beer market is also a key control process to improving the clarity and establishing the product before distribution too. On the first part for fermentation and also for the carbonization and packaging to improve the quality of the product. So let's see the essential guides on tank and process cooling calculation that we search, and next we are going to apply it in a study of case. First of all, we need a detailed description of the overall industry process, of which the cooling phase is a part, how this affects to our objective of the process. Cooling is not an isolated process, but it's a part of a bigger production chain. So it's crucial to understand the impact in the points we are going to offer that cooling. Next, characteristics and quantity of the product to be cooled. Because of each product has a specific thermal capacity, which means that some require energy, more energy to cool than others. For example, liquids with high density and viscosity, such as oil or condensed milk, will require more energy than other lighter liquids, such as water or wine, for example. Next, temperature of the product before and after the cooling process. The temperature difference is a key factor in the calculation of the equipment, because it will affect directly to the cooling capacity that we are going to offer from a cooling processes or even a fermentation process. Time in which we want to cool the product, that time will affect also the cooling capacity required. So faster cooling processes will require a cooling capacity bigger than processes that require a slower cooling processes. Sorry. Environmental condition of the room where the process is carried out. Factors such as ambient temperature, relative humidity, and velocity of the air will affect directly to the coefficient of exchange in the thermal gains that we are going to see. The type of tank, next, number 6, refrigerant in the system. The choice of refrigerant affects directly to the exchange energy efficiency of the process, as well as the tank material use. We will prefer stainless steel tanks that are more thermally efficient. And finally, the use of agitators and other loads according to the processes, such as this agitator, because of we use to promote a better transfer, thermical transfer in the product. We used to avoid the cooled point that could appear due to a non-uniform distribution of the temperature. So with this tool, we can avoid it. So let's see how to calculate tank cooling. At first, we have to consider the gain per wall as the product of the overall wall transfer coefficient. That if the case is there are different coefficient of transfer coefficient for the contour, the floor and the ceiling, we can also divide it into the sum of them. We also have to multiply with the surface, the total surface, and the difference between outside and inside temperature. So now we see the main keys here. For the gain per wall, we will obtain the heat of flux in the time need. Time of the processes. So next we will see the irradiation gain, that is the product of the absorbability of material according to the color. It will be different from a white color or a green color, the absorption is different for that irradiation, thermal solar irradiation. The solar irradiance, typically that is 800 watts per meter square, and the area, the total area. We could also see the sum up of the heat flux from solar irradiation of the contour and the ground. The roof, in este caso, and the roof part. So, if we dive into the cooling heat exchange gain that we need to cooling that process, is the product of the specific heat of the product, the quantity of product to be cooled, the difference between initial and final temperature, and the cooling time. But there is a consideration on cooling. I have to warn here that we cannot assume that a tank will cooling X time just because the calculated cooling capacity assumes so. The reality of the installation is more complex, and we need to have an overall knowledge of the process. As the liquid cools, the thermal gap between the refrigerant and the product decreases, reducing the system ability to extract heat from the tank. This is the case that we are going to dive. Next, this phenomenon belongs to the area of heat transfer in a transient regime, where the variation in temperature affects the speed of cooling. It's not enough to install equipment with the appropriate theoretical power. As a consequence of all of this, it's necessary to analyze the thermal dynamics of the system and the evolution of temperatures. So we have to check for the cooling capacity needs that will be the most, and we also have to check the minimal difference in temperatures in the plate heat exchanger. Next, we are going to check it. In addition, the heat gain through fermentation, in the case we have a process could be the product of the mass flow of fermentation sugar and the heat of fermentation that release that energy of fermentation. In client 316, in the part of tank calculation, we differ from two phases that we can calculate. At first, one phase is one initial transformation from sugar to alcohol by action of those jets that generate heat as a consequence. And a second phase that we could calculate for an addition of sugar to obtain the alcohol that we want. So we have to sizing the system considering the greatest thermal demand from fermentation or cooling processes. So finally, we will have the total cooling capacity, the heat flow through wall transmission. In the case we have outdoor, the heat flow through solar radiation, and the maximum value of heat flow through product cooling or heat flow through fermentation, plus the power absorbed of agitator in the case we have. So the question is, how can we cool the liquid in the desired time? Let's see in this case we will see 4 ways of cooling that. The first one, an example of cooling using 2 tanks and an external heat exchanger. This system allows us a total control of the processes, ensuring a precise cooling because of the temperature, the difference temperature is always the same. So the calculation is more simple. The only disadvantages is that we need economical, and we need 2 tanks and a pumping system unit. So maybe the customer, the client, don't want to choose this non-economical option. Next, we have a cooling process. We can cooling the process with a submerged coil due to the Newton's cooling law. This system is apparently the most economical in terms of installation, and only requires a coil that is submerged in the tank. However, we have disadvantages for the space in the tank and the space of the coil and the heat transfer that we are going to have in this system. That is a big drawback. And according to Newton's law, we have 2 variables, that is time and the refrigerant temperature. That for each refrigerant temperature, we will have a different time of refrigeration. So in the graph that is side on the right, we can establish a calculation time for example of cooling refrigeration. And we see that it's a decreasing logarithmic evolution for temperatures according to the time. Other option, cooling the tank by jackets. That is a system in which the refrigerant liquid tank normally is refrigerated with water or glycol, which circulates through an external layer of the tank and try to extract that heat from the product inside. As it cools the products without the need of submerge, in this case a coil in the liquid. And finally, we will see the cooling for an external heat exchanger. In this case, we will see the plate heat exchanger, and this method consists of recirculating the wine through an external heat exchanger and returning it to the tank after it has been cooled at the temperature that we need. To do this, we have to correct the Newton's law. We change the K, the global coefficient, to a correction that is T, for a better calculation of the process that requires, in this case, several iterations to optimize the flow rates and the thermal exchange to check that the time that we have to, that the time that we are going to cool the whole tank is in the time that we want. It's very important. So let's see the thermal process calculation, how we are going to check it. Heat exchange, a plate heat exchanger is a device that allows us heat to be transferred between both flows. On the one hand, you have a fluid that could be an agri-food fluid. On the other hand, we will have glycol, for example. And mainly a plate heat exchanger is the summary of many thin metal sheets that are stacked one each other. And due to this contact, the heat transfer is very high, and we could transfer very quickly the energy that we have to transfer. Furthermore, these exchangers tend to be very compact, so it's an easy to install, cleaning and maintaining too. So for the installer, it's an easy solution. We have also two main different plate heat exchanger those that are co-current and counter-current flow, where the entry is totally different, and the transmission in the second one will be higher because of the flow is counter, so the overall transfer coefficient is bigger. The main difference for the calculation is that the logarithmic mean temperature difference, in this case, the initial temperature difference are different. At first, in the equicurrent heat flow for a plate heat exchanger, we could use the inlet temperature of the hot fluid, that is, for example, 65 degrees, and the entry of the cool fluid, that could be 25. That is the inlet temperature. But on the other hand, the countercurrent flow, the end of the entry of the hot liquid will be the exit of the cool process fluid. So once we are going to calculate the heat transfer will be different. So, and we will see if we make the calculation that we can obtain a bigger cooling capacity exchange in a countercurrent heat flow than in a concurrent heat flow. It's important to know the movement of the flow. So now we are going to expose an example with Client 360 and how we are going to solve this case. We are going to use the main essential guide on tank cooling that we have shared with you before. In this case, we have to know the process, and the process is going to be for a winery that want to cool the must. They want to ferment the must to transform into wine correctly, and for an efficient cooling security, they are going to make a cooling process for prevent the oxidation and allows to preserve in the better condition, improving the quality of the final wine. So for the dimensioning, we have to know all the variables that we have been talking before. So the main characteristic are these. For a tank volume of 100,000 liters, we are going to have two tanks with a vertical shape. In addition, external condition will be in Córdoba. It will be located, so the ambient temperature will be 35 degrees. It will be also, next we are going to see the layout. It's outside, so we are going to have irradiation, and the insulation will be the contour that will be polyurethane, and the floor and the ceiling in this case it's not isolated. The product first, white must. First in the cooling processes, the first cooling process, we're going to do it in 2 steps, 2 days. So we have a half tank that is 50,000 liters. And for fermentation maintenance, we are going to calculate for more liters. So the installation layout at first could be as we showed here, where the characteristic of the premise is 2. We have also a local volume of 1,050 meters cubic, and we need also a local temperatures of 12 degrees. So we have to select too a cooling air in this case for cooling the premise. So let's see how to calculate this. At first, the first process will be cooling. We have an initial temperature of 30 degrees up to a final temperature of 80 degrees in a time of 10 hours. We will also agitator power, and as we said before, a capacity of 50% of the tank. Next, in the fermentation, we are going to obtain a 15 grade of alcohol. So we will have an initial sugar of 280 grams per liter of must. So we are going to divide it into 2 phases. The final sugar in phase 1 will be 150 liters, and finally there will be empty of sugar. First time will be 8:45 hours, and the second phase will be 72 hours. Finally, the third process will be a cooling from an initial temperature of 18 degrees up to a final temperature of 8 degrees in the time of 10 hours. And finally, we will have a maintenance of a temperature of 8 degrees, where we will have white wine in this case. So let's see how to calculate the processes and the tank cooling. Here in Client 316, I have prepared a project that is cooling tanks calculation that is in my personal area. Let's see the main calculation. For rooms, I have calculate at first the first processes. And this tool, it's located in the left banner, in the part of load calculation, tank cooling. We have to introduce the first part, at first the construction feature, such as the form, the material, the diameter and the height. Next, the external condition that is located in Córdoba for that ambient temperature. That's the isolation that will have our cooling tank. In this case, we select the contour isolation and the material of this isolation, also the thickness. Next, the irradiation because of its outside and the color of both parts. This will be the main for all the processes. And next, the product. In this case, we select must, and we appear the data, the main characteristics of this product, and the process. This case is a cooling. For the need will be the same for warming. It's only addition. I have select the capacity of 50% in an operating time of 10 hours. With this temperature from initial temperature and final temperature, we will obtain a cooling capacity required for cooling that most in that time, from the initial temperature up to the final temperature of 91 kilowatts. It will be our first process. Next, let's see the next processes. The second one, we maintain the same construction, and here we have to select fermentation. As I said before, we are going to do the fermentation at 8 degrees, and we start with 280 grams per liter of sugar, up to 150 grams per liter of sugar in the phase 1. Finally, it's a dry wine, so we won't have any sugar at the end of the phase 2. We can also add the electric power agitator that could be 1 kilowatt for this case. This tool shows us that we need a maximum power of 36 kilowatts in the phase 1. That could be the needs that is bigger for if we consider the phase 1 or the phase 2. So let's see the third process. Up to 8 degrees, that is the next step we have to check, to solve. Now in this case, red wine, it could be, white wine. And the results, that is, we will need a cooling capacity of 92 kilowatts. We will take in consideration for the most cooling capacity need, that will be this one. But first, let's see the worst scenario that is possible for temperature, that is the maintenance of the tank cooling. Where to maintain the product at 8 degrees, we need 8.4 kilowatt. But we are going to check it, as I said before, for the difference of temperature in the plate heat exchange. And how we are going to check it. First, we check it for cooling capacity, that, as we said before, it would be the third process, that is 92 kilowatts. Where in the first side we will have must or wine, in this case. So I select this for the first processes, is the more or less the same need. In the first process we have an inlet temperature of 8 degrees and an outlet temperature of 18 degrees. So we obtain a mass flow of 6.8 meter cubic per hour that will be needs to consider to dimensionize and sizing the pump of the agri-food product. So we are going to revise and check it. On the other hand, we have propylene glycol, 35%. We consider an inlet temperature for the chiller 0 degrees and a loaded temperature of 5 degrees in the side of the plate heat exchanger, and we can see here the graph and the image. Now we have dimensioned it for the total cooling capacity for the worst scenario possible in the case of cooling capacity need, we have to consider too from the worst scenario possible in temperature. If we revise in maintenance, for example, for 8.5 kilowatts, we see how we have to check it. The mass flow in the wine here in the sample is lower, but if we could have, for example, a worse scenario, we will have a bigger mass flow, so our pump could be smaller. So we have to take in consideration all the processes. I know in each step of the process we need a different cooling capacity need, so we have to select now the best equipment for the demand. Okay, so let's see how to select the equipment. As I said before, in the layout installation, we have to cool in the winery, the premise. In this case, we have done a webinar about a load calculation. You could revise in Academy part, in this part, in this button. For example, for that need, we have a 23 kilowatts of cooling capacity need. So we select an air cooler that use propylene glycol at 0 degrees to ensure the temperature of the cool room. This cooling capacity need we have to sum with the need of the worst scenario possible, that was 92 kilowatts, and we have 2 tanks. So the total capacity need will be I have a summary here. Okay, we have 2 cooling tanks with a cooling capacity need of 92 kilowatts, an air cooler of 28 cooling capacity power. So we have a total cooling capacity need of 212 kilowatts. We have to ensure that we could adapt to each step of the process. So we are going to select a full inverter system chiller that, due to the use of a VFD, a variable frequency driver, we can adapt to the demand. We have also used a variable frequency driver in pumps to adapt the propylene glycol flow in each step. So let's see the equipment and how to select that. It's like this. In the part of outdoor units, we could select chillers, and in this case I have calculate for these conditions. At maximum load charge of an inlet temperature of 8 degrees and an outlet temperature of 0 degrees, we obtain a cooling capacity of 289 kilowatts. I have to consider that we could use a recovery heat exchanger in the part of the condensation to thermal heating processes too, that we can on the first part in the evaporator cooling the processes, and we can get free heating due to the heat exchanger in the part of the condensation. If we use the heat recovery of the 100% of cooling of condensation capacity. In next webinar, we will dive into wet water loop systems and chillers, how to sizing them. Finally, thank you so much, and we are going to try to solve any question that you have. So we are going to see the comments if there are any. Pierre asked if we will record the session. Yes, of course, you will have in LinkedIn, and we also have you have access in the part of Client 360 in the button that is of Academy. You could have access, and also in YouTube you could see again from Australia. And for Theory 2, you will have the so Marek, if you have some question about sales, you can ask for the commercial technician. You will keep in touch with him. He could answer your question maybe better than me. So thank you so much. I believe there are no more questions. Marek, how Intarcon delivered any to Poland? Marek, that's other question about sales. I recommend you to keep in touch with the commercial or the team back office of Intarcon that maybe could help better than me in this case. Okay, so thank you so much, and I will see you in next video. If you have any doubt, you can write an email or even could make a video call if you need. So see you next video, next training webinar. Okay, bye.